language extensions. So, we actually talked a little bit about this. We're using these built-in variables such as grid bin, such as block bin. Remember, you saw some of these things in the source code, and these things are really what we call the DIM3 data types. Remember in graphics, okay? In graphics, you have these x, y, z coordinates, right? So this is where CUDA kind of inherited some of the graphics data types, and they may as well just make it available. And this is a kind of a convenient way of declaring the dimensions of the grid and the blocks. Okay, and then each index will be essentially a block index is actually this is only 2 of the 3 dimensions will be used for the block index, and all the 3 dimensions can be used for the thread index within that block. Okay, remember the grid is really just a 2-dimension thing of thread blocks, and each block can be up to 3-dimension thing of threads. So there are also some other common runtime components. One of the things is it's this vector type, and there are some functions that can actually take vector types, like 2D or 3D data type, and simultaneously operate on all the 3 dimensions. And this actually in some cases taps into real hardware that can do the 3-dimension in the same clock cycle and increase throughput. Okay, and there's also a subset of the C runtime library supported in both the host and device codes. So we'll just kind of quickly go over a few of those. So what are the built-in vector types? It turns out that you can have characters, you can have shorts, you can have yins, you can have longs, and you can have floats. Okay, so these are all vectors up to 4 dimensions. Okay, the hardware. Why 4? They can do 4 easily, and usually it's 3 dimensions plus 1 extra 4 dimensions for some of the graphic transformations that people play tricks with. And so, but basically the same kind of computation will be applied to each dimension when you call some of these built-in functions. And DIM3 is really based on unsigned integer 3. So each one is actually an unsigned integer. And you cannot declare a dimension of let's say, a block to be -3. Okay, it's unsigned. Okay, which shouldn't be negative anyway. There are a few things that you will find very useful, and so you have these power, square root, that kind of all these things, exponentials, logs, sine, cosines, and ceiling, floor, and so on. And so what happens with these mathematical functions is that whenever you're executing on a host, a given function uses the C runtime implementation on the host. Okay, remember this. Whenever you use the emulation execution, the emulator is going to use the host C library. Okay? What that means is that you may be using a double precision library without even realizing it. Okay? So you may well be using a double precision implementation with all the extra precisions that you should not expect from the GPU execution at this point, right? Okay? But a lot of people don't realize that. Okay? And these functions are only supported for scalar types, not the vector type. So do not use the built-in vectors with these. They're only going to calculate one value rather than all the 4 values. The fundamental reason is these things are expensive. Okay, so they don't want to do it 4 times all the time, right? They only want to do 1 time on a need basis. So you need to run all the 4 dimensions individually through these functions if you really want to have them all done. So there's some host runtime component that provides functions to do device management. Okay, so you know what, you need to, sometimes you will have multiple GPU cards in one host. So you need to be able to manage multiple of these GPUs. And this, the host runtime does that for you. You need to be able to allocate memory. Remember, in the host code, we actually allocated memory and allocated device memory and all that. So those are the host side, runtime functions. You need to be able to do error handling. Whenever there's a floating point trap in something, the host side runtime would need to, report that. And initialize is first time a runtime function is called, and a host thread can invoke device code only one device. This is another thing that you need to remember. If you want to use multiple GPUs, you need to generate multiple threads on the host. Okay, so you need to generate multiple P threads or use in order to use multiple GPUs. And so that's something that if you're interested in doing this, we can, at some point we can teach you how to do it, but we're not teaching that as part of the lectures. Okay. So from the memory management point of view, these are the host runtime functions that allocate device memory and do the memory copy. Remember, we talked about a few of these, at the beginning. So these are the list of things. And I'm not going to waste time talking about the difference between these things and what's the intricacy and all that. It's not very intricate. It gets a little boring. Last time when I tried, it got really boring after a while. So I'll let you read the documents, and as you pick some of these things, you should read the specifications so that you will pick the right ones. And then you will do, you can actually do some memory addressing. You can actually, get the address for a symbol by calling a runtime memory management function and so on. There's some mathematical functions, such as the trick functions, have less accurate but faster device-only version. Okay, and this is actually executed in hardware in something called special function unit. Okay, and these things can give you very significant performance boost for certain things, especially medical imaging applications. Okay. However, you need to be aware that these hardware functions implementations will give you slightly less number of digits of precision. Okay. So, in some cases, you may not be able to get the result that you want. But for most of the image processing applications, they actually give you pretty much acceptable SNR in the end, or signal-to-noise ratio. Finally, we're talking about the synchronization function here, and I already pretty much explained this in the code. So it appears like a function call, but it actually translates into one machine instruction. Okay, it's one of the intrinsics that that I talk about. It's commonly used, appear like a function in the source code, but translates into essentially one machine instruction. And once all the threads have reached this point, execution resumes normally. Okay, and it's used to avoid read after write, write after write, write after read hazards. Remember, we had two synchronization calls in the matrix multiplication. The first one is used to enforce what we call the read after write dependence, because the code above the synchronization is writing into the shared memory, right? That's write. And then the barrier synchronization followed by all the computation that will be reading from the shared memory. So that's why it's called read after write dependence. Adding that synchronization makes sure that all the writes are complete before any of the reads will start. And that cleanly gives you an enforcement of all the dependencies. Whereas the second synchronization enforces the write after read dependence. Before that second synchronization, all the multiplication adds are reading from the shared memory. And it's blocking the execution from entering the next iteration, which will be writing into the shared memory. So you need to make sure that all the reads are completed before you go and overwrite their operand. So that's called write after read dependencies. Sometimes you'll have write after write, but usually what happens, most frequently you're going to be enforcing either read after write or write after read dependencies. So they're allowed in a conditional constructs only if the conditional is uniform across the entire thread block. This is a little bit of a intricacy. What this really saying is that let's say if you have an if then else, okay, if you choose to do a sync thread, one path, but not the other path, you are treading very dangerous water. Okay, so unless every thread in the block will all go through that same path, either all goes through the then part or all goes through the else part, you can be in very serious trouble in your code. The code will probably just hang, because the code will be expecting every thread, but some of the threads will not show up. Okay, and you don't want to have that kind of situation. It's very hard to debug. It's very hard to detect it. So just as a practice, don't do it.